then phase transitions in the early universe, and quantum field theory and string theory, and also primordial black holes. Similarly, in the late universe, we study dark matter, dark energy, whether Einstein's theory of gravity needs some modification or not, modified gravity, and so on. So if you're interested, you should look into our website. We are also Nottingham is also the home of the famous YouTube channels, for example, 60 Symbols and Number 5. Okay, so coming to the talk, by observing the universe very, very carefully over the past 100 years, we have seen universe has galaxies, and we have seen even further and further away, as it shows in this diagram. We combine different observational tools. For example, we look at how galaxies are clustered. We also look at how supernovae are exploding and how faint they are. We also see the ancient light, which is coming from the very early universe to us today. It's propagating freely, so it carries information about the very early universe. And then Big Bang nucleosynthesis, which I'm calling BBN, which is an epoch which is even earlier than the epoch from which this ancient light is coming to us. This was a time when nuclear physics was important in the universe. The whole universe was plasma, and it was cooking nuclei. And by computing how much helium nucleus, how many number of helium nuclei you produce in today's universe, from that epoch, you can test what was going on at that time. So we have a range of observational tools using which we can study the entire history of the universe. Okay. For example, to give you an update of what we know so far, we know a lot in the last 100 years. We didn't even know in 1924, we didn't even know that there were galaxies outside our Milky Way galaxy. Okay. In fact, exactly 100 years ago, Edwin Hubble discovered that there are these other galaxies. And then slowly we came to know that these galaxies are not only just there, they're going away from each other. Most of the faraway galaxies are going away from each other, which means that the universe is expanding as a function of time. So which means that in the past, universe was denser and denser, and so it will be hotter and hotter, and so it should be in some kind of a soup, okay, plasma soup. So to summarize our knowledge of the early universe, that the very early universe was in a state of hot, dense thermal plasma, and today's universe is a cold and nice structured universe. The early universe was very, very smooth with very little fluctuations here and there, and somehow these fluctuations have grown over the time as the universe expanded and cooled to form all the structure that you see today, including clusters of galaxies, stars, and planets. And in this cosmic history, there are many important epochs, but three of the most important ones, which you will see, for example, in a cosmology textbook, are the following. The first one is Big Bang nucleosynthesis, when the temperature of the universe was as high as more than 1 billion degrees Celsius. Okay, at that time, you can have hydrogen nucleus, another hydrogen nucleus, they can combine and form a helium nucleus. So the first helium and lithium nuclei were formed around that time, and this is called Big Bang nucleosynthesis. Okay. The second thing is, as universe cooled, slowly light could propagate out of this system freely, because then you have neutral atoms. At early times, you have very, very hot, dense plasma. At late times, you have neutral atoms, and neutral atoms are all right because you can see me through my camera, even though there is air molecules here. You can pass through them. So then light sort of propagated, and it's propagating all the way to us from the early universe, carrying all sorts of important information about the universe. Okay, so this light is called cosmic microwave background radiation, and in this talk, I'm going to say it as CMB. Furthermore, late in the universe, we have things called dark matter. Dark matter is a substance which interacts very less with light as well as with electrons and protons. So if dark matter is passing through you, it will just pass through you. However, it has gravitational pull like any other matter. So there's a lot of dark matter. It's more than the amount of standard matter that you know of. Okay? And they clump the universe, and they make it clustered in the form of clusters of galaxies. And finally, towards the present epoch, there is another substance which is called dark energy, which is like a repulsive gravity, which is possible in Einstein's theory. And this is beginning to make our expansion of the universe expand faster and faster. Okay, so it's accelerating the expansion of the universe. In our story today, dark energy won't be that much important, but the rest of the things are important, so we'll keep in mind. Okay, just for terminology, what do we mean by hot Big Bang? It is this early phase of the universe when it was a hot, dense thermal plasma soup. Okay? That's hot Big Bang. It's a phase, it's not an event. It's a timeline, it's a history of the universe. And now we don't have hot, dense plasma soup. We have galaxies and stars and gas molecules, both warm and hot and cold in the universe. Okay, hope that was clear. Okay, now in this talk, we'll think more about the early universe, not today's universe. Our best messenger of the early universe is this cosmic microwave background radiation light. Okay, this is the first light which was able to propagate to us. It is sort of like the surface of sun, for example. If you want to see the interior of sun, you cannot see, right? That's because the light that is produced in the interior of the sun is not able to propagate to you freely. It's doing all sorts of zigzag motion because the interior of sun is actually a plasma. However, the surface, once you reach the surface, from surface, the thickness of plasma decreases. And in fact, then you go to free space, right? Then you can freely propagate out. The same thing happened to light or photons in the early universe, okay? So when you look at these photons with our most advanced camera telescopes, we see that this light is coming to us from all directions. So obviously, it's not coming from one object, it's coming from the whole universe. It's very, very smooth. If you have a thermometer and you want to measure the temperature of this light, you would see that the temperature is 2.7255 in one direction. It will be 2.7255 in another direction. Everywhere the temperature is same up to 4 decimal places. The only deviation starts is at the 5th decimal place. Okay, so if you have a thermometer which could measure 2.72551 or 2.72549, then you would see small difference in the temperature of light coming. And the first satellite which did this was called Kobe here. Then it was done by WMAP, and now the most recent one is called Planck. And you see that the resolution has increased so much that we have seen these fluctuations in temperature all across the sky, very tiny fluctuations, but they are present and we can see them and we can calculate the spot size. Okay, for example, in this diagram, a blue spot means slightly less temperature. A red spot means slightly higher temperature. Okay, so you can see how many spots of cold and hot regions in the sky from this map. So this is our main messenger from the early universe. It's incredible that you can see the early universe through this map. Okay, so what have I learned? I've learned the following: that the early universe was in a hot dense soup, but it had this tiny temperature fluctuations. And once the universe sort of expanded and cooled down, these tiny fluctuations somehow started to grow because gravity started to clump them, okay, with the help of dark matter, for example. And now you have a universe where you have these galaxies and stars and amazing cold and clumpy structured universe. First thing we learned that. Second thing, we know a lot about the nature of these initial fluctuations. Okay? Why were these fluctuations? We want to understand it. Okay, so let's characterize what these fluctuations are. It turns out the fluctuations in all components, electrons, neutrinos, photons, dark matter, whatever was existing in the universe at that time, in all components, you have the same fluctuation to start with. Okay, a physics term for it is called adiabatic fluctuations. So they are adiabatic. Okay. Second, these fluctuations are scale invariant. What does that mean? It means that if you calculate how many spots of cold and hot patches in the sky of size 1 angular, the spot size with you in the sky is 1 degree in the sky, for example. What is the angular size? Let's say fix it to 1 degree. How many 1 degree cold and hot spots we have? Then how many 2 degrees, how many 3 degrees, or even 0.1 degrees, 0.01 degrees, etc. If you compute, they're all the same. Okay, so it's like almost a fractal structure. There's a little bit of deviation from this fractal structure. So 2 things we learned: that these fluctuations are almost scale invariant, the physics term, and there's a little bit of scale dependence, with larger spots are more than smaller spots. Okay, Let's remember this, and that is mathematically represented as this formula here. Third thing, since these are fluctuations, they have some probability of happening, right? So what is the probability distribution from which these fluctuations are being drawn? That also we have measured pretty well, and it seems it's a Gaussian fluctuation, okay? So the probability of finding a particular value of the fluctuation goes as e to the power minus square of that value, okay, with a small variance sigma. Okay. Once in a while, I'll have some maths in the slides, knowing that all of you are interested in physics. But if you find the part of the maths part a bit technical, don't worry about it. You can still understand the talk without it. Okay. And so far, we have not found any deviation from this Gaussian nature of these fluctuations. So great. Now we want to say the large scale structure of the universe as well as the fluctuations in the cosmic microwave background have tiny fluctuations. And our best guess is that quantum mechanics has caused these fluctuations. Okay, the initial fluctuations are caused by quantum mechanics. And quantum mechanics occurring during a particular event in the very early universe, and it's called cosmic inflation, which we'll go to inflation next. Okay? So it produces fluctuations that grow and form galaxies. You can ask, can this inflation create larger fluctuations, which can then form, they can collapse and form black holes in the universe? Okay, so that's the sort of is the theme of this talk. We'll come back to black hole in the second half. Okay, so let's spend about 10 to 15 minutes on this epoch called cosmic inflation, which is supposed to create these fluctuations that you see in this graph. Great. Let me put you in the timeline of the universe so that it will become a little clearer. So usually people would say that at time t equal to 0, there was a singularity which is called Big Bang singularity. This is purely because we are using Einstein's theory of gravity, and we are assuming that we know the history of the universe. That is not correct. At very early times, when the universe was younger than fraction of a second, we don't know what happened, and Einstein's theory is expected to break down. So there is no guarantee that there is a Big Bang singularity. Okay? However, we'll just put that as our time 0 to set our clock. All right. So this did not happen probably. So we have a question mark here. We don't know yet. Then about when the universe was roughly about a few minutes old, the first helium and lithium nuclei were cooked in this plasma state. Okay, that's 3 minutes. And at that time, universe was filled with a lot of light and neutrinos, a lot of radiation. Okay, at some point of time, when the universe was 60,000 years old, it became more dominated by atoms and dark matter. Okay, so that's called matter domination. So radiation domination ended. When it was about 4 lakh years old, 400,000 years old, then it was cold enough that the first atoms started to form. So this ancient light, cosmic microwave background can now propagate. Okay, that's an event about 400,000 years old. The first stars started to form about 1 million years after this time 0. Okay, so when universe was 1 million years old. And today we are talking about amazing stuff in this astronomy bootcamp after roughly about 13.8 billion years old. Okay, so this is quite late. And the early universe sort of combines things of particle physics because it was very high energy and high temperature. So it's just like colliding particles at high energy in Large Hadron Collider, right? So it involves a lot of particle physics, and it's cosmology. We're talking about the universe. So that's the connection between particle physics and cosmology here. Okay, now this cosmic inflation, which I'm talking about, this happened probably around the time when universe was 10 to the power minus 30 seconds old. Okay, so incredibly early in the phase. Okay, so it happened for a fraction of a second and it went away. In this fraction of a second, universe expanded by e to the power 60 times or even higher. Okay, so within a fraction of a second, it was inflated to a big size. E to the power 60 times larger, and then this inflation was over, and then you have the standard hot universe, which expanded and cooled and came to today's universe. Great. Now, next 2 slides may have a bit of more maths, but I'll try to guide you through it. So question is, why would a universe inflate for a fraction of a second? Is it something that we should expect? The answer is yes. The early universe is expected to be filled with many scalar fields. Okay. In particular, the early universe could be filled with something like a Higgs field. Okay, it's not exactly the Higgs field, but it is kind of a Higgs field. And now, sorry, I just want to check one thing. I'm still audible, right?
Yes, sir.
Yes, yes.
Absolutely audible. Yeah.
Yeah, my computer said me something, so that's why I checked.
No,
Great.
no, you're audible.
Okay, so the universe is filled with a uniform scalar field. We call it a scalar field condensate. And the scalar field has a potential. It's sort of, you can think of your Newtonian physics. Okay, if there's a potential and you have a ball can keep rolling, right? So that's what happening is the scalar field. It's everywhere in the universe. It's slowly, its value is slowly decreasing along its potential. As long as it decreases slowly, okay, Einstein's theory of gravity says that a slowly moving scalar field leads to a repulsive gravity. So it expands the space in an accelerated way. In particular, if the kinetic energy of the scalar field, twice of the kinetic energy, remember kinetic energy is half mv square. So for a scalar field, it's half phi dot square. So twice of the kinetic energy is smaller than the potential energy, then the scalar field is moving slowly and then expanding. All right. Now you can ask, why is the scalar field rolling slowly? The answer is the motion of the scalar field in an expanding universe is like the motion of a simple harmonic oscillator, but with a large friction term, which is this blue color. It's coming from the expansion of the universe. And this miraculous letter h is called the Hubble parameter. It's just saying at what rate universe is expanding. Okay? So it gets some friction while it moves. So it moves really slowly initially, and it inflates the universe. After a while, it falls into the potential's minimum, and there it cannot roll slowly anymore because the potential is pulling it very fast now. Okay. So it will now start to oscillate, and universe will no more inflate or accelerate. It will now expand slowly. Okay. But now universe is filled with this scalar field condensate. It's not filled with electrons and protons, etc. This scalar field is dominating the universe, right? However, oscillating scalar field is radioactive, just like Higgs. You produce Higgs in the lab, and very quickly it goes away, right? It emits quarks and photons, etc. Similarly, this oscillating scalar field will emit electrons, photons, all of the standard model particles that you know of. So then this hot Big Bang state begins. Okay. So inflation comes before the hot Big Bang state, but not before the Big Bang singularity. So first Big Bang singularity, which we don't know whether it happened or not, then inflation, and then the hot Big Bang phase, which is a phase of the universe. Great. Now what happens in what we're dealing with is that we have gravity, universe expanding because of gravity, and we have a scalar field. And when you have a scalar field in a accelerating universe, quantum mechanics becomes very, very important. And this we know very well since 1980s, in fact. So you can understand what is quantum mechanics doing to this field. I told you that this field will roll down slowly everywhere in the universe simultaneously, right? However, quantum mechanics causes the field to move slightly differently at different places. So in one way to think is the field doesn't roll like that. Because of quantum fluctuations, the field sort of fluctuates like that. It's your same Heisenberg uncertainty principle, which you may have heard of. Okay. So since it fluctuates, different parts of the universe sort of expands in a different rate. Okay? So when inflation ends, some patches of the universe has become larger and hence less dense. Other parts of the universe has become is relatively smaller, so it's more dense. So once inflation ends, you have this less dense and more dense parts, inhomogeneous paths. Hence, once inflation produces particles, it will be produced hotter or colder in different places, and that creates the initial fluctuations. Okay, so that's the mechanism. What I wanted to say here is that it not only creates these density fluctuations or temperature fluctuations, it also fluctuates the metric of space. Okay, stretches and contracts the space randomly. Overall, the space is expanding, accelerating. But here and there, sometimes it's accelerating more, sometimes it's less. So this more and less acceleration creates tensor fluctuations, technical term, which are basically gravitational waves. So it gives you a background of gravitational waves, which also propagates, apart from these tensor fluctuations. And I'll skip this slide and I'll go to the other slide. So we have so far not seen any gravitational waves from inflation because they're expected to be smaller in amplitude, and our telescopes have not caught up to that yet. However, we have seen these temperature fluctuations in the cosmic microwave background map, which I showed you, very high resolution map by the Planck satellite. And we know the following. We know that these fluctuations are small and they have almost a fractal nature only on the large angular scales in the sky. Okay, if you look at big spot sizes and their fluctuations, they follow, and then slightly smaller spot sizes and their number density and their population, that follows a fractal nature. We have no measurement on spot size which are smaller. Here this blank space is like for very small spot size. We are not able to resolve them. We don't know what they are. So it may be possible that during inflation, the quantum fluctuation once in a while becomes violent. Okay, it's not subtle small fluctuations. Once in a while, it may become violent. If it does become violent, then the small fluctuations that we expect almost fractal-like or almost constant, this green color, can rise a lot, and it can become several orders higher than what you see in the CMB map at very small, very tiny spot sizes. And there, these fluctuations would be important because they are violent enough to collapse a big patch in the universe and make it into a black hole. Okay, so we'll come back to it in a second. So if you think of the potential that I introduced you, it means that this inflaton field was jittering around, okay, slowly and rolling slowly. And suddenly there may be a feature in the potential which makes it to oscillate vigorously. Okay, and these vigorous oscillations will create large fluctuations. Okay, so during inflation, you generally create small fluctuations of long wavelength, as shown here. But at times, you may create large fluctuations of small wavelength. And these fluctuations, when these fluctuations propagate into the hot Big Bang universe, the hot Big Bang universe is made up of plasma. This plasma can collapse. They don't have enough pressure to sustain a violent fluctuation. And this collapse of the plasma really forms so-called black holes, which we call primordial black holes. Okay, now I come to the second part of my talk, which is what are primordial black holes. Okay, so we have learned that the origin of all structure in the universe comes from quantum fluctuations during inflation. In fact, subtle quantum fluctuations during inflation, small fluctuations. And these fluctuations that you create during inflation are sort of propagated into the hot Big Bang plasma, and then the plasma starts to fluctuate, and that's what the temperature fluctuates, and then slowly grow under gravity and form galaxies. Okay. Second thing is, once in a while, these fluctuations, rare fluctuations, could be violent. Okay. To give an example, look at this green color curve. Okay. Suppose it is telling you how the density in the universe is behaving at different space points in the very early times in the universe. Okay. You see most of the density, there's some small variation, but it's almost constant. Okay, you have almost constant density, which is little variation here and there, and most of the variation is happening within 10 to the power -4 or -5. Okay, so density here is 1.00000. Density there is 0.99999. Okay, that's how close they are. That's very uniform. However, once in a while, you have these large density fluctuations. Okay, these large density fluctuations would lead to a collapse of this plasma and form black holes, which I represent by black dots. So rare, vigorous quantum fluctuations from inflation would give rise to primordial black holes. Okay, I'll talk about the history in a second. Now, who was the first person to think in these lines? Okay, great. Now, since many of you are going to do physics in the next few years, or are already doing physics, I should introduce you that how do we discover new laws of physics? New laws appear at higher and higher energies. So to discover new laws of physics, you have to go to higher and higher energies. Okay? For example, since from 1960s till today, we have come from about 1 mega electron volt energy all the way to about 13 tera electron volt energy. Okay, many orders of magnitude, using the Large Hadron Collider, for example. However, we cannot keep building bigger and bigger detectors, because at some point of time it will become bigger than the size of Earth, and we cannot make it. Okay, so we cannot go to arbitrarily high energy scales to discover more fundamental laws, which are more important at the origin of the universe. Okay? However, our universe was hot and dense and very high in temperature at early times. So that is our natural lab, and whatever happened in the universe is inside the universe. You should be a careful detective to look at how galaxies are clustered today, how this cosmic microwave background fluctuation is behaving, to carefully predict what was going on in the early universe. Okay? Apart from that, you also have gravitational waves, and they can propagate from the very early times in the hot Big Bang phase to today. Right? So looking at them carefully, you can discern what's going on in the universe. We have some idea of, so in this plot, on my right side is the today's universe. Okay, I'm not showing it. I'm showing only the early history of the universe. So there was a time when the nuclei started to form, right? They were cooked in the Big Bang nucleosynthesis. Before that, what happened? We don't have much idea. We have some idea about what this inflaton field, inflation scalar field was doing, how it was jittering around for a very specific short time in the history of the universe. But most of the times are question marks, as you see. How exactly the inflaton field decayed to form the hot Big Bang phase is called reheating. We don't know how it happened. How did inflation begin? We don't know. Whether there was a Big Bang singularity, we don't know. Lots of interesting questions. But what I wanted to say is you can know what happened by carefully looking at the universe. Now I'll move on and talk about primordial black holes. So in the last more than 30 minutes, I have talked about early universe. Now in the next 20 minutes, I'll talk about, maybe 15 minutes, I'll talk about black holes. Okay. Now, if you go to a person in 1960s and say the word black holes, they would get scared and think you are doing crazy or exotic physics. Terms like that would be used. I should say that Pink Floyd has a song called Shine On You, Crazy Diamond, and they have the word black hole in it in the astrophysical context in 1975. Okay, so that's quite great. So at least some people were open to it, but most people were not. However, today, now in 21st century, we have seen many black holes. Nobel Prizes have been given in the last few years, and it's the most exciting and hot topic in all of physics today. Okay. Now, what is a black hole? A black hole has very complex geometry in Einstein's theory. For today's talk, thankfully, the complex geometry around a black hole won't be that important because we're looking at cosmological black holes. So we're looking at them far away. We're looking how many of them are there in the universe, how they are distributed, rather than going close and zooming into a particular black hole. Okay. So for us, we will think of a black hole as a spherical object whose radius is the so-called Schwarzschild radius of a black hole. It's related to 2g and mass of the black hole divided by speed of light square. Okay, this is the radius of a black hole. It's a compact object. And what could be its mass? In general, physics allows it to have any mass. For example, it could be as low as Planck mass, 10 to the power minus 5 gram, and as high as 10 to the power 50 gram, like cluster of galaxies or something. Okay, so it could have any mass. What have we seen so far? We have seen black holes. We have seen compact objects called neutron stars, which are about 2 times mass of our sun. Okay. Then we have seen small black holes slightly higher than the neutron star mass, about 5 to 70, 80 solar mass. Okay, a solar mass, let me remind you, is the mass of our sun. We think of sun as a typical star, and hence we talk about mass of black holes in terms of mass of sun. Okay, when I say 10 solar mass, it means the mass of the black hole is 10 times higher than mass of our sun, which is 10 to the power 33 gram, which is quite a massive object. We have seen supermassive black holes whose mass is about 1,000,000 times larger than our sun, to 1 billion or even 10 billion times massive than our sun. Okay, so huge, humongous black holes we have seen. So far, we haven't seen any black hole whose mass is in between 200 solar mass and 10,000 solar mass. We haven't yet. Okay. Now, black holes can be divided into two parts. One, astrophysical black holes that are formed when the fuel which is burning a star is over and gravity crushes the star to form a black hole. Okay, so these are called astrophysical black holes. They're formed from the death of a star, and hence these black holes, astrophysical black holes, are stellar graveyard. It turns out if the mass of a star is not much greater than 3 solar mass, it doesn't have enough gravity to collapse to a black hole. So astrophysical black holes are expected to have a mass roughly greater than 3 solar mass. Then there are these cosmological black holes I told you, which forms from the collapse of plasma in the early universe. They could have any mass. Okay, they don't form from stars. They have nothing to do with stars. So they could have any mass. What kind of black holes have we seen? If I go into a bit detail, using so if one black hole finds another black hole, they rotate around each other because of gravity, and then at some point of time they collide. Okay, and both during their rotation as well as their collision, they emit gravitational waves, which we have caught, let's say, by using the LIGO, Virgo detectors that are there in the US and in Italy. And we have seen about 100 such collision events. So we have seen two black holes colliding, giving rise to another black hole. Two neutron stars colliding, giving rise to a black hole. One black hole, one neutron star colliding and giving rise to a black hole. All sorts of possibilities. Okay, and they span from about 5 solar mass to about 160 solar mass. So we've seen lots of them. A Nobel Prize was given for this work. And using radio telescope, using many radio telescopes to use a big part of the Earth as an entire radio detector, we have seen a black hole at the center of a galaxy called M87. It's a gargantuan black hole. It is sort of like the black hole you have seen in Interstellar. It is 6 billion solar mass. Okay, it's huge. And what you see here in this image are the hot gas and substance around this star, which is emitting radio waves, and sorry, around the black hole. And the big black hole is here, right? This dark spot at the center of this dark spot. Okay, so we have seen them, these humongous ones. This network of radio telescopes that are used to detect this is called Event Horizon telescopes. Now, zooming back to primordial black holes, these are black holes that are formed in the early universe, and at a time when the universe was much younger than about a minute. Okay? I don't know if you have read Steven Weinberg's famous book, First 3 Minutes, the first popular cosmology book, which talks about how nuclei were cooked. Similarly, these black holes would have formed before that time, okay? The black holes that I'm talking about. So really early. They're formed when the universe was radiation dominated. So it was in the hot Big Bang phase. And they have nothing to do with stars, as I've told you. So their mass could vary between a Planck mass to the cluster of galaxy mass, basically. Okay. Astrophysically, you might wonder why primordial black holes can form within a second, while standard stellar black holes form after 1 million years. The answer is because to form a black hole from a star, you have to wait until first a star is formed. Since the initial fluctuations were mostly small, a star gets formed in the universe after 1 million years. So you have to wait for a long time to see the first black holes in the universe, in astrophysically. Okay, cosmologically, that's not the case. Great. So what are their implications? First of all, since they're formed in the early universe, if you detect them today, you know they carry information about the early universe, like looking at their mass and how many of them are there. You can understand what was going on in the early universe, how vigorous were the fluctuations, for example. Okay? So they give you access to very high energy physics, which you cannot access by using Large Hadron Collider. Second, they are a natural candidate for dark matter. I said dark matter is necessary to form structure and galaxies, and we are almost 99.79 times percent sure that there is dark matter in the universe. We just don't know what it is, and maybe these primordial black holes are dark matter. They have been there for a while, and they're very tiny. They're compact objects, so they behave for all purpose. They behave like dark matter. Okay, and they are our only hope to probe Hawking radiation, which I'll explain in the next slide. So let's skip that for now. They can help you understand what was going on, what was happening during inflation when the inflaton field was rolling down and inflation is about to end. Okay, so that's called small scale primordial physics. It helps you to do that. We have many supermassive black holes in the early universe, and we don't know how to explain them by looking at how stars would die and form them, okay, because they're forming very early. So we think that these supermassive black holes might have been seeded by primordial black holes, which were existing, and then they started to accrete matter around them and grew to form supermassive black holes. They can also explain matter-antimatter asymmetry in the universe. They can also explain origin of all matter after inflation. These 2 points, I will not talk about it, but ask me if you have a question on this. Great. So who thought of primordial black holes first? Well, there was a group in Russia, Zeldovich and Novikov. They thought of maybe in early universe, if fluctuations are vigorous, then they might grow and form big black holes. Okay, but we don't see so many black holes, so maybe that didn't happen. There was a very important paper which got Stephen Hawking thinking, and he realized that no, it's not necessary that these black holes would grow. You can form tiny black holes and they may not grow very fast. Okay, so you should be fine. So that was the original theoretical discovery, 1970. Now, once that Hawking figured out that there are these small black holes, then he said if black holes are small, quantum mechanics may be important for them, right? So then he started thinking about what is the quantum mechanics of black holes. And that led Hawking to his greatest discovery, the so-called Hawking radiation. By thinking carefully how quantum fields behave around a black hole, Hawking found that if you have a black hole, quantum fluctuations will lead to leak or decay of particles from the black hole. So the black hole mass will reduce, its size will reduce, and eventually the black hole will completely vanish. Okay, and this giving rise to radiation, and this is called Hawking radiation. This is probably one of the most important papers that was written in the last century in physics, and as you know how famous it is. So in this regard, I would like to tell you something about how the view of black hole has changed. Okay, one of the pioneers of black hole physics is Indian scientist Chandrasekhar Subramaniam, who was mostly a classical physicist but a brilliant physicist. And he had a quote saying black holes are the most perfect objects. Once you form, they're almost spherical. They don't have any random so-called hair in them, and they're absolutely beautiful objects, classical objects. He's correct. This is true for big black holes. However, if black holes are small, quantum effects are important. These black holes are not going to hang out forever. They are not eternal. Once you form a black hole, for example, here, once you form a black hole, classical black hole, its size sort of remains fixed, and with time, it just goes into time. In a sense, it's a fixed size, and you can propagate it through time from early times to today. However, in what Hawking discovered that no, quantum mechanics would lead to leakage of radiation from these black holes, initially long wavelength radiation. Then as the black hole becomes shorter, even shorter wavelength or high energy radiation. And at the end, the black hole will completely explode with large energy emission, okay, like let's say gamma rays emission, for example. And it'll evaporate completely. It has a finite lifetime. Okay, so that's our new view of a black hole. Okay. Another interesting thing is that Hawking radiation has a temperature. It's a thermal radiation. It's not a random radiation. It's roughly a thermal radiation, which means that the number of photons of a given frequency is given by the thermodynamic distribution or the Planck distribution. Okay, and a thermal distribution is described in terms of its temperature of these photons. Okay, the cosmic microwave background radiation is also thermal radiation. That's why it has a temperature, which I was quoting, 2.7255 Kelvin. Now, Hawking temperature is very, very important in physics because it has got all four fundamental constants that we use or you have used in your college and undergrad course. It has Planck's constant h cross. It has speed of light c/c^3. It has Newton's gravity constant g, as well as it has Boltzmann's constant k. So it's thermodynamics, it's gravity, it's quantum mechanics, and it's relativity, all of it combined. Okay, so that's the Hawking temperature formula. And the Hawking temperature of a black hole is inversely proportional to the mass of the black hole. Okay, so a smaller black hole has a higher Hawking temperature, and the Hawking temperature of a solar mass black hole, let's say, if we take our sun and compress it to form a black hole, its Hawking temperature would be 10 to the power minus 7 Kelvin. Okay, which means you cannot detect it. It's a very low temperature. So that's why we have never discovered Hawking radiation so far, and Hawking died without getting a Nobel Prize, for example. Okay. Since they radiate, they will evaporate eventually, and the evaporation time is about 10 to the power 10 years if the black hole has a mass 10 to the power 15 gram. Okay, so if you take a Himalaya mountain, compress it to form a black hole, and this black hole will last for about 10 billion years, age of our universe. Okay. If black holes are larger than that, they can last longer and humongously longer. A solar mass black hole will last for 10 to the power 67 years. Okay, that's low is the Hawking radiation. But small black holes have a shorter lifetime. So if you form a very small black hole, they can evaporate quickly, and you can see the Hawking radiation out of it. For example, if the mass of a black hole is less than 10 to the power 9 grams, these black holes will evaporate before the first nuclei were cooked in the hot Big Bang phase. Okay? So you cannot see them because they will evaporate and form lots of photons, they will thermalize. It's very difficult to see them. Another interesting fact, if a primordial black hole has a temperature, will have a temperature same as our cosmic microwave background light if its mass is about 10 to the power 25 grams. It's roughly about mass of the our moon, right? Our satellite moon. So if you take moon and compress it to a black hole, it will emit a light which is similar to the cosmic microwave background light that we see. So very interesting. Okay, and inflation says that these black holes, if they form because of vigorous fluctuations from inflation, their mass has to be greater than 10 to the power minus 2 gram. It's a detail, but don't worry about it. Lots of pioneering work was done in 1970s, as you can see from these references. Great. So since it's a black body, it has a black body spectrum, and this spectrum obeys the Wien's displacement law, which you might remember from your course, which means that the wavelength is inversely proportional to temperature, hence it's inversely proportional to the mass, okay, the peak wavelength. So a black hole of 10 to the power minus 8 solar mass will radiate in between microwave and infrared. A black hole of roughly 10 to the power minus 13 solar mass will emit around UV or X-ray. A black hole of 10 to the power minus 16 solar mass will emit gamma ray, and even smaller black holes will emit gamma rays as well as other particles, can produce quarks and electrons out of it if the temperature is low enough. Okay, so this is super interesting. Okay. Now, when do these black holes form? In cosmologically, if they're forming during the Big Bang, the mass of these black holes are related to the time when they form. For example, a black hole which is formed roughly around 1 second after the Big Bang will have about 60,000 solar mass. Okay, so you can form a 60,000 solar mass black hole within 1 second after Big Bang. So they're quite powerful. So this hot Big Bang phase is a powerful machine which can produce lots of black holes. A solar mass black hole would have formed about a microsecond after the Big Bang. Okay. Similarly, a Himalaya mass black hole would have formed about 10 to the power minus 23 seconds after the Big Bang. So they're telling you about what was going on in the universe so early. Okay. Radius of a black hole, which I told you is called the Schwarzschild radius, which is related to its mass. A bigger black hole are bigger in size. Heavier black holes are bigger in size, naturally. A black hole whose mass is same as mass of our sun has about 3 kilometer size, okay, or 3,000 meters, so 3 kilometer size. That means you want to convert your sun to a black hole, you have to compress the entire big sun to only 3 kilometer size, okay, radius. Then, similarly, if a black hole's mass is smaller than a satellite or an asteroid mass, then these black holes are microscopic in size. That's why quantum mechanics becomes so important. Right? If the black holes are about 10 to the power 15 gram Himalaya mass, then you have to compress them to a size of a proton. Then it can become a black hole. So just keep these numbers in mind. Similarly, black holes are much smaller than 10 solar mass. They don't accrete much light in the early universe. So if they're formed by, let's say, Earth mass black hole, very tiny but Earth mass, then it will remain the same size. It won't accrete and grow. So it behaves like dark matter, basically. Okay, last few things about black holes. This is the time when they form is related to their mass after the Big Bang. Just to give you some numbers, if this gargantuan black hole image that I showed you, supermassive black hole image, this so-called image of a black hole, that's 6 billion solar mass, okay? And if this was a primordial black hole, then it would have formed about 3 hours after the Big Bang. It is not a primordial black hole, but I'm just giving you a number. As you know, its size, as you probably know, its size is about size of our solar system. Okay, so big black hole. Huge. This is the black hole where in interstellar they fell into. Okay. Then solar mass black hole, okay, 10 to the power 33 gram, are 3 kilometer in size, and they would have formed about a microsecond after the Big Bang. Earth mass black holes have about 1 centimeter size or so, and they were formed about 10 to the power minus 12 seconds after the Big Bang, and so on. Okay, so just keep these numbers. Okay, now we're coming to the end of the talk. Now you can ask, where are these black holes? if they're formed in during the Big Bang, where are they? Well, since they are natural candidates of dark matter, they should be where dark matter are. So we can ask, where are dark matter in the universe? We know that if when you look at a galaxy here, the dark matter is like a halo surrounding this galaxy, in a big sphere around that galaxy. Okay, this fuzzy thing. So if dark matter is made up of black holes, then there are lots of black holes here around the galaxy outside. Okay? So we have some constraints already. For example, this is a constraint coming from a paper which was which had an important contribution from Nottingham. Um, we know that if the black holes are very small, they would have evaporated by now, so they cannot be dark matter because dark matter is still present. If the black holes are too big, all the shaded region here are ruled out. Okay, what this y-axis is saying is how many black holes you can have, and the x-axis is saying is their mass. So if the black holes are big, then if you look at, let's say, Andromeda galaxy, and these black holes are passing through you, then you would see that these black holes will bend light towards your telescope. So you would see an increase in light for microlensing. Okay, and we have not seen much. So from there we know that we have a bound on how many of these black holes are there. Okay, for example, they can at max be 1% of the total dark matter abundance. So we have lots of bound, but we also have lots of free space. For example, here, asteroid mass black holes could be all of dark matter in the universe. So also keep that in mind. Okay, this is probably my last slide. Is okay, so if these black holes are around a galaxy, can I see them in our solar system? Well, you can actually calculate. We know the mass of dark matter around our galaxy. Okay, we know that mass. Take that mass. Think of a black hole of a given mass. Here I'm thinking of a black hole of 10 to the power 21 gram. So if we divide the entire mass with this mass of a single black hole, then we know how many black holes are expected. Okay, and you can find that there are about 10 to the power 24 Avogadro number of black holes that are expected in the entire halo around the Milky Way galaxy at max. Is that a big number? 10 to the power 24 seems to be a big number. Well, this is same as the number of gas molecules here in my hand as I make this imaginary volume in my hand. So it's not much. In the entire Milky Way galaxy halo, there are only 10 to the power 24 primordial black holes. So do not expect them to bump into our solar system or to land in your backyard someday. So it's difficult. So you have to look for them very, very carefully. Okay, so that's what we have been doing. We have been looking at searching for these black holes using different telescopes, different detectors, electromagnetic waves, radio waves, gamma rays, all electromagnetic spectrum, all of it, as well as gravitational waves, and whether these black holes can accrete and explode once in a while. Let's say a black hole gets absorbed into a star or a white dwarf or a neutron star, and it can accrete their material and make it explode, right? So we're looking for all of these events very, very carefully. These black holes can have a range of masses, while what we have seen in astrophysical black holes are a very small range of all possible mass. So in the coming few decades, the search or the hunt for primordial black holes will be more systematic, given that we have more detectors and telescopes coming up. So watch out for this. Please feel free to ask me questions now, later, anytime you think. You can know more about primordial black holes inflation from, let's say, the 6 Symbols YouTube channel. If you want to know it technically, then I can provide some links to study them. I provide my email ID. Feel free to email me also. I'll stop speaking here. Thank you.
Thank you, Swagata, first of all, for coming to our platform, and during this boot camp, you've shared such a brilliant presentation. I think it have given little insight related to the topic to all the budding people who wanted to pursue their careers in astronomy and astrophysics. So we already have some questions in the chat.
Sure. Yeah. I can have a look at that. Prerna, is it okay if you read it out to me? It'd be
Yeah,
easier.
yeah, because it's
Lovely.
coming scrolling. I'm just scrolling.
Wonderful.
Actually. So, Yesh Jain, sir, since we can't see before CMB, how do we know that these events happen and how do we know the time of the period? Time of
Yeah,
this period of formation radiation.
that is a excellent question. I'm very happy that somebody asked this question. So light is able to propagate from here to us. Okay, this is the time when the CMB light started propagating. So you can think that, okay, all we can know about the universe is from here to there. How do you know something happened before? Okay, great question. The answer is the following. First of all, it's not just light that we see to predict what's going on in the universe. There could be relics left over that was cooked or created in a phase prior to this phase when light started coming. For example, Big Bang nucleosynthesis cooks nuclei. Okay, and you can count how many helium and lithium nuclei we have in the universe, and then you can know exactly what was going on during Big Bang. Okay, so this is a cosmic detective. Not only looks at light, but it also looks at relics. This is very similar to archaeology, right? When you try to find out what was going on in Harappan civilization, you don't see the light coming from Harappan people to you. What you see is leftover utensils, jewelries and stuff. So similarly, Big Bang nucleosynthesis is an example where relics would help you to know. Second relics that we talk today are primordial black holes. If there are primordial black holes, you will know. The third thing, apart from light, there are other things that propagate to you. For example, neutrinos propagate to you. Here in this green color things are neutrinos. They propagate to you from an earlier epoch than the epoch from which light propagates. Okay, so by looking carefully at neutrinos, you can know what was going on even earlier. And ultimately, you have gravitational waves. They are not hindered by anything. So once gravitational waves are emitted by anything in the early universe, they just propagate freely to you, right? So you can look at gravitational waves and know what's going on in the universe. In fact, just yesterday, I just completed a work on how to figure out what was going on in the universe by looking at gravitational waves. So I hope that is clear now.
I hope, yes, you got the clarity on your question. If
Yes,
anything
ma'am.
left,
Yes, ma'am.
please.
Thank you, sir.
Yeah, thank you. We'll move to the next. Shivam Sharma. It's theorized from the various particle physics models with the help of laboratories like CERN.
Mhm.
Ma'am,
Yeah, who's this?
ma'am,
Yeah, please,
hello.
please. Yeah, please go ahead.
Yeah, ma'am, I would request students that they should unmute themselves and ask their own questions
I
for the.
appreciate that. I
Yeah.
appreciate
So
that because,
instead of
yeah,
you reading them, reading
yes,
questions for
I
them, I
definitely,
request
definitely.
everyone who has got the questions that they should mute themselves and ask the questions directly from the sir.
They are free to do that, and we appreciate
Shivam,
that if
please
they can ask.
unmute yourself
Yeah,
and ask questions.
because it's your question, you should ask, and in case you need any other inputs on that, so then there and then you can ask that.
Okay, so am I audible?
Yes, you're audible, Shivam.
Yes.
Go ahead.
Good afternoon, sir. So my question was, are gravitational wave observatories like LIGO the ultimate key to understand to the dark ages of the universe, as gravity is the only thing which can move around those distances?
Very good. Um, yeah. So let me first make it clear before answering the question. Dark ages is an age of the universe between the time when the first atoms formed or this cosmic microwave background was emitted and the first star were formed. This is called dark ages. Okay, and as you see, this is not really dark because cosmic microwave background is propagating through this epoch, right? Okay, so you can probe dark epoch by using electromagnetic radiation. There's something called 21 centimeter radiation. It's doing to do with transition, hyperfine splitting of hydrogen atom and transitions of photons between them. That leads to a radio signal, 21 centimeter. So dark ages is not a problem at all. It can be easily probed. Uh, if by dark age you meant something before this CMB light, That was not dark. The universe was extremely hot and dense and plasma. It was hot. It's like sun. Okay, even hotter than sun. So, but from there, light cannot propagate. The neutrinos can propagate, and of course, gravity, as you pointed out correctly, gravitational waves would easily propagate through all of them and come to you. Okay. Now, whether LIGO can do it, if the level of these gravitational waves is much higher, then LIGO can do it. We expect the level of gravitational waves to be much lower. The gravitational waves from early universe to be much lower compared to gravitational waves that are emitted by lots of stars rotating around each other, binary stars and binary white dwarfs and neutron stars, things like that. So LIGO may not be able to do it, but future gravitational wave detectors, such as LISA or Big Bang Observer or Cosmic Explorer, Einstein Telescope, things like that would be able to do it better. But we would
Sir,
need.
are these observatories space based, like placed at somewhere L2 point, like JWST, to increase the accuracy or precision?
Good question. Unfortunately, I don't have a detector, so you'll have to hear my word without a figure. So, for
All right.
example, LISA is a space-based, and so as some of the other planned ones, for example, DESIGO and Big Bang Observer (BBO). They are not granted. LISA is granted; it will come for sure. Okay. Now, there are some which are very good sensitivity, and they're also Earth-based. For example, Cosmic Explorer and Einstein Telescope. There will be big telescopes on Earth, not in the sky. So they're a mixture of ground-based and space-based telescopes. Okay.
All right. Thank you, sir.
Wonderful.
Satish, you can ask the question. Actually, while writing, the question goes into the pieces and then chat goes up and on. So probably some of the text I missed while reading. So it's really good idea if you can ask your questions yourself. Satish, we can take your question. Please open your mic. You
Hello,
can.
am
Yeah.
I audible, ma'am? Hello.
Yes. Yes, you're audible. Please.
So, sir, good afternoon, sir. So, my question
Hi.
is that if you talk about the Big Bang singularity at that time, the space-time curvature is like so bent, it tends to infinity. So, we we have known so far now is that uh, nothing can escape from its gravity, like in case of black hole. So, how is it possible to uh, that universe has expanded from its own gravity? Like,
Very good. Good question. Yeah. First of all, if you were present during the early part of my talk, I mentioned that this the fact that there is a Big Bang singularity is purely Einstein's theory of gravity combined with assuming that you know what was going on in the universe. First of all, what we know for sure is Einstein's gravity will break down that. Okay, there will be new theories. This is very similar to, there were these similar singularities in electromagnetic theory, in the study of how electrons behave when it emits a photon in 1900s early. And it was, the minute quantum mechanics came, it was gone completely. Okay, so it was these singularities are artifacts of classical physics. They're not quantum physics. Okay. Second, I should add that this Big Bang singularity is different from a singularity of a black hole at the center of a black hole. Okay, a black hole singularity is surrounded by a horizon. A Big Bang singularity doesn't have that kind of horizon. It's in some sense it's a naked singularity. Okay, it's not the same as a black hole singularity. But yes, classical Einstein's theory predicts there is a singularity. We do not believe, none of us believe there is a singularity. We know that something new will come, and that's what we're using. We just use that term to set our time t equal to 0. That's all. Okay, that's why you see there is a question mark there. It's not true.
okay, thank you, sir.
Yeah.
So we'll move to the next question. Harshvardhan, you can please ask.
Yes, ma'am. Thank you, ma'am. Good evening. Good evening, sir. Sir, my question was about the Hawking radiations. Sir, is it an actual detectable radiation or is it just one of those tricks that we add to just fit the theory? Like the information paradox raised the question that if something falls into a black hole, where does its information suddenly disappear? So, is Hawking radiation an actual radiation or is it just to fit go around that the shortcomings?
Yeah, I think the question comes from a misunderstanding. So let me explain. First of all, Hawking radiation is as robust as predicting how I know Casimir effect works, which we have tested in lab. Okay, or lamp shift, things like that. Okay, so it's not some exotic physics. It's just basic thermodynamics, quantum field theory, and gravity combined. So it's a very robust prediction. We all think this is correct. Okay, there may be correction to it if you do better calculation, but the level at which Hawking did, this is correct. Now, this was not introduced to explain information paradox. Rather, it's other way around. The fact that there is Hawking radiation, it leads to a information paradox. So let me explain what information paradox is. Some people think information paradox is the fact that whatever goes inside a black hole, it falls inside a black hole, so information is lost. Does that mean that if I lock a 1 rupee coin in a box, that coin is lost? No, it's inside the box, right? So that's not information paradox. Information paradox is the following. You can make something fall into a black hole, so it's gone into the black hole, it's not lost, it's there inside the black hole. Now you wait for a long time, there is Hawking radiation, so the black hole will completely radiate. Okay? You put a 1 rupee coin into it, the black hole radiates, and after some time it completely evaporates. As it evaporates completely, it has given rise to this thermal radiation. So you put a 1 rupee coin, what came out is pure thermal radiation. Your friend would have thrown a cricket ball into it, right? If your friend would wait for a long time, then the black hole will completely evaporate into thermal radiation, the same thermal radiation. Okay, so that means whether a coin went into a black hole or a cricket ball went into a black hole, what comes out once the black hole is evaporated seems to be pure thermal radiation, and this is the information paradox. Okay, the information paradox is a consequence of Hawking radiation, not the other way around. Now, how do we think about it in modern physics? We think of it is that the radiation that's coming out is not exactly thermal. It's roughly thermal up to some uh, average calculation. If we can do a better calculation, we will see that there are subtle differences which can tell you whether a coin fell in or a ball fell. Is that clear now? You should take
Yes,
the calculation of Hawking radiation as seriously as you take hydrogen atom transitions.
yes, sir. So, sir, if we have to entangle particles and one of them falls in, so can we predict? Can we measure what's going on inside the black hole from the change in state of the other entangled particle which we are having, because the states of the two entangled particles will be uh,
Good. Yeah,
related to
good.
each other.
Hmm. Yeah, so in principle, we can someday, not yet. This is the question of not measuring, it's just calculating also, right? We don't know, the calculation is tough here. So in principle, yes, we can do someday, not yet. Okay, unless I know the exact microstates of the black hole. If I know what the black hole is, what are its microstates, we don't know it. We explain black hole using thermodynamics. So how it forms, all we explain is using gross properties or thermodynamic properties. If we know its microstate, its statistical mechanics, then we can do that. So you can do it for some black hole in principle, not yet. So we have to understand quantum gravity better to understand what is the structure of this black hole. Maybe we don't need quantum gravity. Maybe we just need to do a better calculation of Hawking radiation, and things are uh, the information of the second particle is somehow encoded into the higher point fluctuations of this radiation that's coming out. So it's thermal plus some corrections, and the informations are in those corrections. Okay.
Yes, sir. And sir, is there any estimate on the like we can say photon comes out of the sun and will reach us 8.5 minutes later. So is there any estimate like if a particle falls into the black
Yeah.
hole right now, till when can we get back its Hawking radiation signal back?
Yeah, that's pretty well known. Huh? Yeah. It can completely evaporate. We know the evaporation time. For example, in this slide, I've quoted. It takes 10 to the power 10 years for a Himalaya mass black hole. It takes 10 to the power 67 years for a solar mass black hole. So that's pretty well known.
Okay, thanks.
The next question we can take Vivek, yours. You have posted two questions. Please, you can ask. Vivek, are you here? If not, then I can read it. He has written the question: when light cannot escape black holes gravity, then how can relativistic jet escape gravity? Also, earlier he asked, "Hello,
I
sir.
Mhm.
What will happen to?" Okay, you are here, Vivek. What will happen to black holes at the end? So these two questions he has posted.
Mm, yeah, I'm not sure I understand. I mean, light can come out of gravity. It's not. You can see sun, even the sun is pulling the photons. The difference is that the wavelength of light or the frequency of light when it was emitted would be different from when you detect it. And for sun, it will be very slight, non-negligible difference. While for a black hole, it's a huge difference, right? The same happens to not just to wavelength of light, but also happens to age of people. Somebody who stays in a rocket outside a black hole or a star, and somebody who goes towards the surface and comes back, like man's planet in Interstellar, right? The time would be different. Yeah, this comes from just a potential difference. It's at the surface and later on. This happens to Earth. It'll happen to an object which moves away from me and comes back. Right? It's just that the effects will be low in normal objects, and it will be amplified in a compact object like a neutron star or a black hole.
I think he is a bad signal, so he unable to speak. No worries. I've read your question. Any other question? If anyone have, please go ahead.
Yes, ma'am.
Please go ahead.
Sir, could the initial fluctuations which you're talking about, you were relating those two fractals. So they might have originated from the processes or dimensions like beyond our familiar like 3D with like spatial dimensions. Like if so, how do scientists explore or interpret those higher dimensional effects? If
Yeah, very good. It could be okay. What we know is that what we think we know is that these fluctuations were created during inflation. Okay, the inflation needs an inflaton field, which is a scalar field, to create this fluctuation. This part we know. If you compute what's the fluctuations during inflation, it matches exactly with what you have seen. Okay, so that's a great thing. Now you can ask, what is this inflaton field, this scalar field? Is it another scalar field in our normal 3D like a Higgs field, or it's an effect of extra dimension, the size of the dimension or something which is appearing to a 3D?
Thank you. So Vivek wanted to ask one more question because he has posted it earlier.
Yeah,
What will happen to black holes at the end? This was his initial question, I think, during the talk.
yeah, there are two answers to it. Mm, the standard answer, as per Hawking's calculation and what I think most physicists believe, is that toward the end stage it will become smaller and smaller. So it will emit higher and higher frequency or high energy particles, and that's why. Well, I have shown here one paper of Hawking, which is called Particle Creation by Black Holes. In the same year, he had another paper in Nature, which is called Black Hole Explosions. Okay? It will basically explode in some sense, and most physicists believe that's what will happen. Some physicists think that maybe as the black hole becomes Planck size, its size is Planck length, 10 to the power minus 35 meters. Okay? There, some quantum gravity effects will kick in and will stop the black hole from emitting. That could happen, for example. I personally am open to both, mm, but for now, it seems like the black hole emission is purely a classical gravity and quantum field theory effect. So I would, if I have to vote, I'll vote probably it will completely evaporate. But we need to understand the microstructure of a black hole, the quantum mechanical structure of a black hole, much more to be 100% sure what happens. Okay? But what Hawking said will still be valid for most part of the black hole, for most of its lifetime. Maybe towards the end, maybe there are some changes. Is that clear?
Hope Vivek you got the clarity on the question. Okay, he said thank you. So do we have other questions? I think
Yes, ma'am.
yeah, please go ahead because I can't see new question in the chat. Please open your mic and feel free to ask.
Yeah. So my question is related to gravitational waves. Yesterday we had a session with Sanjeev sir, and
Uh,
gravitational waves just
Sorry, with whom?
am I
I couldn't
audible?
hear. Yes,
with
yesterday
with
you had a
Sanjeev with Sanjeev Dhurandhar from Ayuka. We had the
Sanjeev.
session yesterday. Yeah.
Great, great. Yeah, Sanjeev. Yeah.
Yeah. So that was again on gravitational waves, and there he told us, I have the doubt, and in response to that, he told us that just like other waves, gravitational waves will keep on losing amplitude as the distance from the source keeps on increasing, and with time it will have to go out as well. So, seeing that any gravitational wave from the Big Bang to we've had like 13.8 billion years from that. How is it possible that a gravitational wave from that time is still existing?
Well, I didn't understand. What would happen to the gravitational wave? Where would it vanish?
So,
It cannot be absorbed,
so
right?
it can't be absorbed, but as it passes out, its amplitude will keep on
Oh, absolutely.
decreasing.
Yes, yes. Very good. Yes. Of course, its amplitude will be much lower than what you saw, and its frequency will also be different. Suppose it was emitted as a high frequency gravitational wave, it will become low frequency gravitational wave. That's all. You see that these space-based detectors, for example, LISA, it's you know, it will be in the sky. It will have three arms, sort of a triangle, and this is a big distance. Okay, so they will be sensitive. They can easily measure gravitational waves of millimeter. How to say? Milli electron volt. I'm trying to convert it into the frequency. The frequency, which is much smaller, 1,000 times smaller than millihertz frequency. Okay, so it's 1,000 times smaller than LIGO frequencies. Okay, so you have 1,000 times longer wavelength. And similarly, you can use an array of pulsars in the sky, which are even further than this LISA satellite, right? And these pulsars are very good keeper of time. So as they rotate, they're like lighthouse. So you see these beams coming to you from all directions. But these pulsars are surrounded over a light year distance or even higher from us. So if you see a network of pulsars, and if a gravitational wave passes through them, long wavelength, like this is what you're worried about. The wavelength has become long. But if they pass through these pulsars, and then in one direction the light will come to you quicker, and the other direction the light will come slower, and so you will see them in pulsar timing array. So you can see nanohertz signal, so 1 billion times larger wavelength signals than LIGO. Similarly, you can use cosmic microwave background to see even long wavelength gravitational waves. What they would do, they would create a particular type of polarization in the CMB light called B mode polarization. So early universe gravitational waves, when they produce, they have all sorts of frequencies. These all sorts of frequencies will propagate. As they propagate, the frequency will become lower or the wavelength will become larger. But then we'll use all sorts of detectors. Einstein telescope cosmic explorer, which are kilohertz, hertz frequency range. LISA, which is millihertz. And then pulsar timing array, which is nanohertz. And CMB, which is 10 to the power minus whatever, 16 hertz or so. Is that okay?
Yes,
And the amplitude will
just
be
one.
lower. You're right. Yeah.
Yes. So one last question: that how would we differentiate, or how would we uh, d- uh, calculate or decide that this is from the Big Bang, because we have a lot of other gravitational waves which are still coming from Big Bang.
Yeah. I wish I had a slide. Let me try. Huh? Give me a second. Maybe I have a slide. Let me try. Okay, maybe I have a slide, so I can show you. This is from a very recent paper of mine, and I need to go quite down to show you a signal. Okay. How would we know? Yeah, maybe I'll stick here. What you see is the amplitude of gravitational waves as a function of frequency, and these are different detectors, whatever different detectors can see. The inflation, the gravitational waves that's coming from, let's say, inflation has a particular signal like this. Okay, a gravitational waves which comes from something else. Let me show you an example. In case this allows me to. So, for example, there's so-called gravitational waves from first order phase transitions. Okay, they will have a signal sort of like that. Okay, Then let's say gravitational waves from cosmic strings, they would have a different signature. They probably have a signature like that. There's something called scalar induced gravitational waves. They are produced from large density fluctuations. They would have a signature like that. Sorry, my software didn't do that correctly. But you understand that the signal would be different as a function of frequency. So if you see the signal in different frequencies, pulsar timing array, LISA, DESIGO, LIGO, etc., then you can discern what it is. The predicted signal will be different for different processes.
Okay, so we have predicted the signal. How would it look? What would it
Yes.
look like?
Yes, so that's what we are doing as theorists now. We're trying to predict all possible signals that could be there from the early universe. And then as these advanced gravitational wave detectors come up in the next generation, they would then test them carefully. Good question.
Thank you, sir.
Yeah.
Do we have other questions? Anyone would like to ask any doubts?
Sir, can white holes be existed as described in Penrose diagram?
Whether they can exist or not, I don't know. It's sort of like going backward in time. It's like particle and antiparticle. Whether they exist as in the sense of would we see a region of space where things are falling into it? So far not. They can, yes, I think they can exist. Whether there was a process which formed a black hole and a white hole, both of them present in our same universe, we don't know.
So
Yeah,
if they exist, how can we detect them?
Yeah, because you'll see these points in space, they're like small regions, compact regions where things are falling a lot, right? They become very hot and dense and high temperature. We don't know. To my knowledge, there is no astronomical observation whose best explanation are white dwarfs. I mean, there are regions like AGNs, etc., but we know these are black holes accreting matter. There are supernovae, we know stars colliding, collapsing. So, yeah, I would say not yet observational. I think it's not too crazy theoretically, but not yet.
So is there a possibility to meet our fellow parallel universe beings like in the black hole, like with reference to the Penrose diagram? Like it shows that we have a common black hole, like the parallel universe and the universe we are living in.
I don't know. For that we have to detect a parallel universe, and I mean it's possible. Okay, it doesn't violate some laws of physics. It's difficult usually to have a bridge which is how to say, stable enough so that it lets you pass through it. Yeah, I don't know. I don't even know whether there are parallel universes, right? Maybe. Yeah.
Yes.
Do we have other questions? I think this was the one of the. Yeah, please go ahead.
One more question that's been bugging me. Can we take gargantuan black holes, if not small or supermassive black holes, as some sort of puncture in space-time fabric?
Well, first of all, space-time is not a fabric. I mean, it has curvature. That's why we use the term. I don't think I would have used in my talk ever the word fabric, but okay, maybe. But it's not like a fabric is made up of, it's made up of molecules. Okay, so you can make a puncture. So it's probably okay to say school children that yeah, black hole is like some kind of singularity in the fabric. So it's not too off. But so far I wouldn't think of space as a fabric. It may have microstructure, by the way. It's quite possible that it has a Planck length microstructure, but I don't think it's like a fabric. So these properties like its pressure and tension and shear, etc., that are there in fabrics and also in space-time, is emerging from some kind of quantum gravity dynamics inside. So yeah, in that sense, it's okay. But for now, we should not think of black holes as punctures. We should think of them as sinkholes. and sinkholes where space is constantly flowing inside. Okay, that's a better picture of a black hole. And once you cross the event horizon, the flow is like greater than speed of light. So if you once cross that point, you are bound to fall into the sink. Now, what happens exactly at the sink center? It's another singularity, and this definitely requires quantum gravity, which we don't know yet.
Thank you,
Yeah,
sir.
I personally don't think of black hole as a puncture, but it's not too, yeah, it's not too bad either.
Okay, sir.
Sir, sir,
Yeah, please go ahead, Harshvardhan.
sir, if we look at gravitational force on the lines of energy field instead of a force field, so would it be correct to say that using E is equal to h nu, there would be some threshold above which the photons can escape the potential, well, the
Correct.
gravitational potential, well?
I think that's correct. You can think of, in fact, you should not think of them as force. You should think of in terms of potential. They think that the surface of a black hole, there is a high gravitational potential, and as you come across outside, the potential is low. So if a photon is emitted at the surface and you are detecting somewhat far outside, then the energy of the photon would be less, because it has to come out of the potential. It's just like when you climb a mountain, you get tired. So that's exactly correct.
Thank you, sir.
Yeah.
Sir, can gravitational waves perturb the space-time curvature already existing there?
100%. Very good. Yes. Gravitational waves, when we pass through, let's say it was emitted in a collision of two black holes far away. As it passes through, it perturbs the curvature of space-time. Yes.
So, like, sir, we have a scenario like a giant, uh, supergiant, supergiant sun, like it's about to collapse in its own gravity and about to become a black hole.
Mhm.
So before that, a gravitational waves came and hit that curvature.
Very interesting question. Unfortunately, yeah, it's very difficult to generate. In principle, yes, it's still possible. Let's say a star was going to collapse, but a gravitational wave sort of rips it apart or stabilizes it for a while. Possible, but you need that kind of strong gravitational wave. It's very difficult. Okay, to give you an example, when two big black holes collide and give you gravitational waves, it can move uh, uh, a distance of 10 to the power minus 21 meter of a 1 meter stick. Okay, so if a 1 meter stick, it only perturbs by 10 to the power minus 21 meters, very tiny. So yeah, you should not expect that to happen. In principle, it can, but it's tough to emit a strong gravitational waves, basically.
Okay, thank you, sir.
Yeah.
Anyone else? I think this was really
Great.
insightful talk for all the participants. They have really got so much to think. So, yes, Satish, we wanted to ask something. So, no more question. I think, sir, on that
Yeah.
note, we'll wrap today's session.
Yeah,
Thank you once.
thank you very much. Hope I lived up to your expectations, and hope the camp goes super well for everybody. My
Yes,
best wishes.
definitely, sir. Thank you for your time. Despite of so much time zone differences, I think we could manage most of the speakers to speak during this boot camp, and I think this is really like very helpful for all the participants because they all are undergraduation students majorly. So it will help them a lot in terms of thinking for some subjects and topic we have chosen in this boot camp. So thank you once again for speaking on the Planetarium's platform, and we really look forward for more such engaging session in future as well.
Now, cheers. Good day to everybody. Yeah. Bye bye.
Bye and take care to yourself. Thank you.